Data is going out. Huzzah! We're online, at least in one place, waiting for Twitch. Come on, Twitch. I want you to connect. Hey. Ooh. Oh, come on, Switch. All right. Bola. Awesome. ET's time. So. Main screen. Turn on. Oh, for goodness sake. Bop. Bob, why is that suddenly invisible? Oh, right. Because I should really change. Bam. There we go. There we go. Oh. For the love of Pete. Hey, there it is. Kazoom! Ba-boom! There it is. Boop, boop, ba-doop, ba-doo. Yeah, it's time for this show. Alright, let's begin. So, let's turn the mic down a smidgen. And we're about ready to begin. So, welcome back to Rocket Science for the Complete Beginner. Sorry for the delay. A blizzard kept me in Phoenix, and the hotel Wi-Fi was insufficient for the streaming needs. So everything got delayed. But anyway, let's begin. We'll review what we did last time, and then we'll go from there. So last time, the sort of big concept, or one of them anyway, was that if some quantity S is changing at a constant rate R, then the amount of stuff that you accumulate t seconds later is just S equals R times t. And say, for example, if that is distance from some point, then you would have D equals RT, and that's where we get the Dart McGart. Wu-Tang forever! Anyway. But anyway, the examples we talked about that are in particular very interesting to us regarding mechanics are velocity, right? And we can say that velocity, the amount of velocity we accumulate is equal to that rate, the acceleration, right? Acceleration is the rate here, and V is what is being accumulated. And T just tells us, if we're accumulating stuff at this rate for this long, V is how much stuff we'll have. So here's another example. So distance is equal to velocity times time. Well, what does that mean? That means if we're traveling in the same direction at this constant velocity t for this many hours t, or seconds, or however long, then the distance we accumulate over that time is d. Yeah, nothing too exciting. But this is wild, man. Here's some good stuff. So we also saw that if we are to graph, for example, the acceleration curve, which on Earth is simply the constant function, negative 9.8 meters per second squared, right? It's this negative orange function here. It just goes on forever. It's a constant. It doesn't matter how much time goes on, unless a significant portion of the Earth is suddenly cast off into deep space. That that's always going to be the acceleration. So the constant acceleration, we saw this also last week, corresponds on our graph to a horizontal line, right? Because it's not changing. No matter what time it is, it's always pulling you down at the same rate. And then, for example, if you drop an object near the surface of Earth, within 50 miles or whatever of the surface, it's going to fall about, well, that's maybe not quite that far, but let's say within a couple miles of the surface of the Earth, and you drop an object, 2 seconds later, its velocity, right, will be just the acceleration, a sub g, times the time it's traveling at that acceleration, right? This is the rate of change, and this is how long it's changing at that rate. And so this velocity here is the total amount we accumulated, right? Like as this acceleration is acting on the object, it's accumulating velocity, downward velocity. As time goes by, play it again, Sam. What's also beautiful is the existential delight of canceling units, right? This all makes sense, right? If we multiply this acceleration, meters per second squared, times a time in seconds, the seconds will cancel and we'll be left with meters per single second, not seconds squared, right? It's good stuff. Quality. So let's start, let's think about gravity and let's push things a little further, right? So we know, like, if we go back, right, we have this simple equation that relates velocity to acceleration and time. Yeah? So let's go farther. Let's ask a more interesting question. So today's question is, we probably won't get to all of it today, but we'll get to some of it. We'll answer at least part of this question today. So if we throw a ball into the air directly upward, and it's got an initial velocity v naught meters per second, it's pronounced v naught when you see that v underscore 0. And generally speaking in physics, if you see something underscore 0, it typically means when the time is 0, or like when whatever it is, whatever phenomenon you're studying, the moment that you set to 0, when the stopwatch begins, right? That's your 0. And oftentimes, and we'll see this throughout the course as we go on, it's often the case that it's useful to choose that 0 point in different ways. Like sometimes you might want the 0 to be, the moment after you threw the ball. Or potentially it's possible, depending on the situation, you might want to have the 0 point be a few seconds before or after, depending on whatever sort of other circumstances are out there. But anyway, so anytime we see that v underscore 0, it means that the velocity, it doesn't mean the velocity is 0. It simply means that whatever v naught is, that's the speed when our time, whenever we start our stopwatch, is 0, right? So we want to know, how can we determine the ball's velocity, right? So we know last week we did if we just drop something off a cliff, right? Gravity starts acting on it and it just goes down faster and faster. But here we have a more interesting problem. What if we throw something up in the air instead of just dropping it, right? So we want to know, what is the ball's velocity at any given time? And what's going to prove to be a little bit more of a challenge is determining the ball's height at some later point. So essentially we want to know, like, how long is the ball in the air? How high does it go? These are all questions so we want to be able to answer. So we want to develop some sort of theory for throwing stuff in the air. So let's just think about it, right? I mean, we go back to our same equation. It's the same exact thing, right? Forgive me, I didn't put units here. I should have put units in. But I forgot. You might even say I forgot. Anyway, so we already have the tools for this first question, right? Because we know, right, the first part of the question is, how can we determine the ball's velocity, right, at however many seconds have gone by? Well, we already know how to do this because gravity is traveling at a constant, well, it's not traveling, gravity accelerates at a constant rate, right? So this is the example, again, where if we drop the boulder, right, it's 0 meters per second, and then gravity acts on it for 1 second, 2 seconds, and its velocity increases in magnitude in the downward direction. Yeah. And we can, so we'll get back to this first question, right? Like, we'll get to this, but let's revisit this one first and just sort of remember what we know, and we can graph it, yeah? So there's a lot going on this slide, admittedly. So let's forget about the top for a second, and let's just look here. So this graph, as time is increasing, this is the velocity axis here. So we know that when 0 seconds have passed, right, the instant I let go of the boulder, it isn't moving at all because gravity hasn't had a chance to start pulling it down yet. 1 second later, gravity has been acting on the boulder for 1 second, and now it's traveling at negative 9.8 meters per second. 2 seconds later, the boulder's fallen even farther, and it's now traveling negative 19.6 meters per second. And after 3 seconds, it's going negative 29.4 meters per second. Right? And this will continue. Again, we're sort of neglecting air resistance here, right? I mean, if we were in a vacuum, this is exactly how it would go. And you would just keep going, assuming you had a sufficiently deep pit. You would just keep going faster and faster and faster. We'll talk about air resistance and stuff like that maybe at some point, but for our purposes, it's really not that important, at least not right now. But the reason I included all of these things up here is I want you to notice something. I want to remind us of something that we talked about last week, and in fact, it was one of the biggest sort of topics from last week, was this notion that we can think of the area underneath the acceleration curve, right? This orange curve is the acceleration curve here. It's the negative 9.8 meters per second squared. This is just the constant acceleration of gravity, right? And if I look at the area between the curve and the horizontal axis, that gives me the velocity, right? Like after 1 second, the area underneath this curve is 1 second, the width, times negative 9.8 meters per second squared, which is the height. Yeah? And the same thing happens for the 2 seconds after the boulder is dropped, and again for 3 seconds after the boulder is dropped, right? And I want to make this point again because we're going to utilize this notion of area later to figure out the height, right? We're going to, again, if we go back to this graph, right here we have the acceleration graph. The area between the graph and the curve is the accumulation velocity. And so eventually what we're going to do is we're going to use that same idea. We're going to take the area under the graph of the velocity curve to find the accumulated distance. So that'll be what we're going to work towards. Yeah. So we're going to use this exact same idea. Here, calculating the area is very easy because it's just rectangles, right? And they correspond, right, to these points on the graph here. Yeah. So we saw in the last example that the velocity of an object dropped from some cliff is equal to the product of the acceleration of gravity and the time for which the ball has been falling. But now we're going to answer this more interesting question, the one that we posed for today. This is the big question for today. And it's now, in this case, we're going to throw a ball upward, directly upward. So what I mean by that is all this velocity is going straight upwards, right? The ball wasn't thrown at an angle and it's not going forwards and up, it's going straight up. If you want, you could say it's not even a human doing it, like you take a pitching machine and put it on its side and it's shooting balls straight into the air, right? And its initial velocity, vertically speaking, is a positive 19.6 meters per second. So this means, again, note that the positive number indicates an upward direction. Excuse me, I gotta get a glass of water here. Read the slide. Focus. Okay. So, right. We were just saying, right, so the initial velocity is 19.6 meters per second. And remember, this is a vector. So the positive number means that this is going upwards, right? So our v naught, right? This is the velocity the moment the ball begins traveling upwards, i.e. when the time is 0. So we're starting our stopwatch the instant the ball goes up. But just like always, gravity is accelerating the ball downwards at this constant negative 9.8 meters per second, right? And so what that means, per second squared, excuse me. So what that means is that for every second that passes, the velocity of the ball is going to change by negative 9.8 meters per second. Yeah? So in particular, here's an example. So v sub 1, this is the velocity 1 second after the ball is thrown. Well, that's exactly equal to whatever the original velocity was. And since it's been 1 second, well, now the velocity will change by negative 9.8 meters per second. And that's exactly because the gravity on Earth is, or the acceleration of gravity on Earth is negative 9.8 meters per second squared. And that means that every second that passes, it's changing by this much. And so because we've changed 1 second, we're decreasing, or it's not decreasing, it's changing by this much. It's not good to say decreasing. I mean, at this point in time, the speed is decreasing. But we're talking about velocity here. And so the velocity is changing, right? And it changes in this very convenient way. It's almost like these numbers were chosen on purpose, but the idea is, right, that in this 1 second that passes between the moment the ball is thrown and 1 second later, the speed of the ball decreases by 9.8 meters per second from 19.6 meters per second to 9.8 meters per second. Notice that this is positive, right? So the ball is still traveling upwards. So let's work on filling out a table of values, right? Let's continue on. So if we look at this one, let's look at what happens between seconds 1 and 2. So we know that when t equals 0, the ball is traveling 19.6 meters per second upwards. 1 second later, gravity has slowed it down. It's now traveling 9.8 meters per second upwards. And now between the the end of second 1 and the end of second 2, right? The ball's velocity is again going to change by negative 9.8 meters per second. So 2 seconds later, after the ball is thrown, right, it's going to be whatever the speed was after 1 second minus another 9.8 meters per second. Right? That's exactly what that acceleration means. It means that for every second that goes by, the velocity changes by negative 9.8 meters per second. So I'm doing a little algebra trickery here. Instead of just writing, like, I know that this number right here is positive 9.8, right? Because we already calculated this in the last slide, right? We know that V1 is equal to 9.8, but I think it's useful to instead write it this way, right? I mean, I can also write V1 like this. And I'm doing it to try and illustrate the pattern here. Notice that if I'm losing 9.8 meters per second every second, then after 2 seconds, well, I've lost exactly 2 times that much. Or I got to break the habit of saying decrease and losing. So if I change by this negative 9.8 meters per second every second, right, then after 2 seconds, I've changed by exactly twice that amount. And the reason for that is because this gravity is a constant rate. Right? We'll get to situations where accelerations and things like that are changing, and that just all bets are off. Like, stuff gets way, way weirder. But because acceleration is constant, we get this nice affine relationship here. So notice that after 1 second, it's the initial velocity times 1 of these negative 9.8 meters per second. The velocity after 2 seconds is the original velocity minus 2 of these 9.8 meters per second. And at this point, after we've lost 2 of those, we're at 0. So this calculation says that 2 seconds after the ball is thrown into the air, its velocity is 0 meters per second. This means that the ball is neither traveling upwards nor downwards. So what does that mean? So the ball goes up, right? Up until this point, the speed of the ball has been positive, right? It's been going upwards. And then all of a sudden, the ball reaches a speed of 0. So what do you think this 2 seconds represents? Like 2 seconds after the ball is thrown up, the velocity is 0. So there's two possibilities, right? I mean, now either our equation is incredibly sophisticated, and it somehow knows exactly when the ball hits the ground and the velocity becomes 0. But I don't think there's anything to indicate that. In fact, there's not. In fact, more to the point, as we'll see in the next slide, once more time goes by, that's clearly not what happens. So it can't be that. So the ball can't be on the ground. So it has to be something else. And what could it be? Isn't it neat? Wouldn't you say my collection's complete? Aren't I the ball that has everything? I don't know. Whatever. Anyway, so yeah, let's think about, keep that in mind. What do you think that 2 seconds is? It's not when it's on the ground. It has to be something else. Something. If you don't know, that's okay. We'll figure it out together. Let's do another couple just for fun. Or maybe just one more. So once again, I'm going to do this algebra trick again, right? I know that in between second 2 and second 3, the ball's velocity will again change by negative 9.8 meters per second. And so it's the velocity 3 seconds after the ball is thrown will be whatever the velocity was 2 seconds after the ball was thrown, minus 9.8 meters per second squared, per second, sorry. Gosh darn it, there's a typo. Typos. That's just embarrassing. Well, at least they didn't go all the way through. Anyway, sorry about the typos. Just need to do a little wham, sad face. Sorry about that. Anyway, but anyway, it's the same thing, right? So the units are a mistake, and I apologize for that, but forgive me. But anyway, so these should be meters per second. I apologize. It's a typo, but anyway, the point is we lose another negative. We change by another negative 9.8 meters per second, and that means that now our original upward velocity was 19.6 meters per second. But gravity has pulled on us for long enough now that our velocity has now become negative, which means that the ball is falling down. The room is spinning around. My stomach is making funny sounds. Anyway, so again, we get the same pattern, right? It's the initial upward velocity minus this 9.8 meters per second times the number of seconds that it's been since the ball was thrown. And so we can see that this pattern is going to continue, right? Like this velocity just keeps changing by negative 9.8 for every second that passes, right? It's positive 19.6, then it changes by negative 9.8 to positive 9.8. Then that changes from positive 9.8 to 0 to negative 9.8 to negative 19.6. And again, the only reason for this is because the acceleration of Earth's gravity is constant. It's always the same. So now we can plot these points on a graph and we can get a feel for what the velocity does as a function of time. Right? We know that it's going to have this nice formula here. And again, the cunning mathematician uses clever observation to enact laziness. A la the Green Goblin, right? The cunning warrior attacks neither the head nor the mind. The heart, Osborne. Whatever. Anyway, notice that the velocity, right? So we can make this nice little formula here, right? I mean, I just yapped about this for a while, but this is the idea, right? We have this constant acceleration of gravity, and we saw from observation here, like doing these calculations over and over again, right, for for 1 and for 2 and then again for 3. We saw that it's always the same. It's a constant change. And so that constant change is illustrated right here. This t is our variable, right? Because, well, as we'll see, both t and v are variables. Later on, we'll get to that notion. But for now, just notice the idea is that, we have this relationship. That the amount of velocity that is accumulated is equal to how much you started from and then how much you accumulate at this constant rate, right? So assuming we start with some positive amount and then we start accumulating this negative amount, well, that means we're going to start going down. Yeah. So now we have two equations, right? We have two fundamental equations. Maybe they're not that interesting, but this first one here, we have an equation for the acceleration of gravity. It's this constant. Notice there's no variables. It's just a constant. This is fixed. And we have this nice equation right here for the velocity of an object with some initial velocity t seconds after it's thrown or dropped or whatever, right? The point is, we're getting closer, right? We want to answer all these questions about height and how fast things are going at different times and all these different things. Well, now we have the velocity set done. This will tell you whatever you need to know, right? And with these powers, we could conquer gravity itself. We could be a superhero. Fight crime. Or whatever. But first, whatever. Man, I had all these great jokes lined up, and then, that was 2 days ago, and I forgot them all. My sadness, the winter of my discontent. Yeah, 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 yeah. Whatever. Cool. So, aside, all this nonsense down here aside, we still don't really know that much about the height yet. And though I don't think I mentioned it, let's go back to this real quick. Let's finish off this. So clearly, this when the velocity is 0, that actually represents the maximum height. And that's not real surprising, right? You throw a ball up in the air, it's going up, but it starts slowing down. It hits a maximum height, and in the instant it hits that maximum height, it has no velocity up or down. It has one brief moment of pure and complete stillness before it falls back to Earth, right? So at least we know one thing. We know when the object, if thrown upward, reaches its maximum height. And it's precisely when the velocity is 0. So here are some general velocity graphs. You shall know our velocity, friend. That was an okay book. I don't know. I guess it's good to travel. Whatever. Anyway, so here's some velocity graphs with curves. So I'm just going to use this term thrown in quotations here, because thrown could mean fired from a cannon, thrown by a person, I don't know, being ejected from a volcano, or whatever. Just something that is, has an initial velocity of something, or just something that's allowed to be acted on by gravity. So, for example, this blue graph right here, this indicates that the initial velocity, right, v naught of the blue graph, is 29.4 meters per second. So this graph right here charts what happens to this object t seconds after it's thrown into the air, right? So the ball's thrown into the air at this speed. After this many seconds, the velocity reaches 0. And so this would represent the time at which the ball reaches its maximum height. Notice we still don't know when, or what that height is, I should say. We have no idea what that height is. We'll work towards figuring it out, and we should figure it out by the end of today. But as of right now, we don't know what that is. Similarly, here's a ball that's thrown up in the air at 14 meters per second. So it's still thrown upwards. Note that both of these are positive, right? So these represent the ball going up in the air to start, right? So the ball goes up in the air. And I know it's weird to think about, but this whole time between here and here, the ball is going higher and higher and higher. Right? So the ball is going higher, 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 until the velocity reaches 0, right here, right? The ball is at its maximum height. And then as gravity keeps acting on it, the velocity becomes negative and becomes more and more negative, which means not only does it start falling down, but it starts falling faster and faster and faster, right? The orange one here, this is the case where we drop something, right? And then this is the case where something is thrown downward. I think after I'm reading all of this, or not reading it, but after saying all of this, I'm pretty sure I typed all that out. But let's talk about these graphs. So notice one thing with all of them. Notice that all of these functions, right, they all have the same structure. The only thing that's different is the initial velocity, right? And so the idea here is that because of this constant of gravity, it doesn't matter. The only thing that really changes the gravity function for velocity is your initial velocity. And that determines everything. Because gravity is constant. Or the acceleration of it, I should say. And so in math, we call this, these are affine functions here. And so this constant rate of change we call the slope in math. You've probably seen that term in algebra, right? Like y equals mx plus b. Well, in this case, a sub g is that m. Yep. And we can extend this notion to say that affine functions with the same rate of change will have parallel lines for graphs. So what this means is these lines are all parallel because these objects are all being acted on by the same constant of gravity. And another way to say that in mathing terms is that two lines are parallel if and only if they have the same slopes, right? The idea is that if they weren't changing at the same steepness, eventually they would run into each other. But since they're changing at the same rate, they shall always be forever apart. So like I was saying before, the blue and red graphs represent scenarios in which an object begins with an upward velocity. In both of these cases, the object travels upwards until it slows to a stop before beginning its descent towards the Earth. The maximum height is achieved when the vertical velocity of the object is precisely 0. And then the orange graph is when an object is dropped, and the purple graph is where it has a downward velocity. So imagine if you're on a cliff, like sort of leaning over the side, and you just hurled a ball down. Oh, kind of hurl his own ball at him. How spectacular. Speaking of spectacular, I just want to real quick. That's the Lost Coast of California. I held a Mamiya RB67 that entire trip, which is what this photo was taken upon. Anyway, beautiful place. That was many years ago when I was a younger man. Whatever. So what we know right now, so let's get back to our problem of the height, right? So we figured out the velocity question, right? We can figure out the velocity at any time, regardless of whether it's thrown up or thrown down or dropped. And we know that if it's thrown upward, then the maximum height will be achieved precisely when the velocity is 0. But we don't know what that height is. We know that's when it happens. We got to figure out what it is. All right. So, for example, here's an example of, right, we can always find when this happens. Yeah. We've done this calculation, or we can do it again. So what you see here is that we just use our equation again. This is our velocity equation, right? We derived this. That's supposed to be t seconds. I'm going to get rid of that. But there's going to make a few little edits here to the PDF before I post it. But the idea is, right, this is the same equation for everything. In this case, our initial velocity is a positive 29.4. right? Which means that you're throwing it upwards at 29.4 meters per second. Well, it turns out that after 3 seconds, your velocity will equal 0, right? Because 3 times negative 9.8 equals negative 29.4. And so we know that if you throw a ball at that speed upwards, it will take 3 seconds to reach its maximum height. But we still don't know what that maximum height is, and we need to find a way to do it. So let's do one that we don't know the answer to right away. I'm like, wait, Walter's advice. So here's one we don't already know, right? So let's take that equation. Let's look at the red graph here, right? Here's our red function, right? So this is where we throw the ball upwards at 14 meters per second. Yep. So to find when this reaches its maximum height, we want to mark it 0. Entering a world of pain. Mark it 0. Right? So if we want to find when this part equals 0, we'll just set it equal to 0. Mark it 0. Let me nobody in the Jesus. Whatever. So anyway, so let's find out when v is equal to 0. Just set it equal to 0. Right? This is the old algebra trickery. Algebra's coming in to make your day. So, for example, we want to know when it's 0 meters per second. Well, we just set the velocity equal to 0 meters per second, and then we solve for the time t that makes that true, right? God damn it, the typos. The frickin' typos. Yeah. Okay, so those typos mean that we're just going to do this one by hand, is what that means. So, let's do it. Yeah, you go. Let's just do it by hand because I am dumb. So we know that v equals negative 9.8 meters per second squared times t plus 14 meters per second. Right? And we want to find when it's 0. Well, we need to find this guy. Oh man, I'm so thirsty. Anyway, so how can we find that? Well, we got to do algebra. So we subtract let's add negative 14 meters per second to both sides. And then these guys go blorp. And so we have negative 14 meters per second equals negative 9.8 meters per second squared times t. And then what does this mean? Well, so let's be careful here. So let's just so we need to multiply by the exact reciprocal of this. So we got to flip everything. So I know I'm going to have something over negative 9.8 meters, and the second squared will go up here. And we'll multiply this by the same thing. And now we have a canceling bonanza. Bing ding 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 ding. Crazy Jim's canceling bonanza is at hand. 9.8, 9.8 meters are all gone. Second squared out of hand. Ding 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 ding. The left side only hand. Ding ding ding. Shit. There we go. And then on the right, well, what happens? Well, the meters cancel. This second cancels with the squareds, and we get the negatives also cancel, so we get 14 over 9.8 seconds are all that's left. And that's good because time is equal to seconds, and this equals approximately 1.4286. And I'm just a silly boy. So forget that. Ugh. I'll fix that and then post the PDF. Ugh. Always typos. Always typos. So many. Anyway. But we don't have to do this computation every time, right? Like, we can just do it generally. It's always going to work out the same. And it's always going to be that. So the maximum height, well, it's not always going to be that. It's going to always be this. So yeah. So to save ourselves doing that computation every time, we can use this formula below. So if an object is thrown, again, quote unquote, it could be a cannon fired straight into the air, or, as we'll see later, it's really just whatever the initial vertical velocity of an object is. Assuming it has an upward initial vertical velocity, the maximum height will be achieved precisely at this value. And the people rejoice as was prophesied. People sing now. La-ba-da-ba-da-ba-doo. So this is the problem. We celebrate, but we still have this problem, right? This is the second half of that first question, right? We answered the velocity bit, and we know when the ball reaches its maximum height, but we got to figure out what the maximum height is. And also, we want a height formula because we might want to know what is the height of the ball 1.5 seconds later or something like that. So we know the object achieves its maximum height, but we don't know what that actual height is, like I just said. You know, and assuming this object were large or sharp or on fire, like that stupid, God, what's his name? Rob Lowe, 911 show. They've been advertising during all the football games, and that firefighter gets hit by that, like, flaming stone. God, TV is so bad. Anyway, assuming this object were large or sharp or whatever, like, you might want to know how much time you have to get out of the way if it's, like, falling towards you, right? And so we need a height function. We're going to work towards that. But for now, we need to think about the relationship between Shai Hulud and the spice melange. But really, it's that notion of area again. We're going to go back to area. So here again, we can see, right, if we take the acceleration graph, then velocity corresponds to area between the graph and the axis. Now, in this case, you could say, well, that's coincidence, right, Brett? Because this just happens to be rectangles, and area just happens to be length times width, and the formula just happens to be AG times T, and, okay, yeah, maybe, that's whatever. But, I mean, you would be wrong, but we'll get into it. This video, we're running out of time here, but in the next video, I'll get into the details of why area under the velocity curve corresponds to height. It's pretty cool, I think. But anyway, so here's our velocity graph, right? That's whatever. Anyway, yeah, and we know that if we have an initial upward velocity of 29.4 meters per second, we know that 3 seconds later, the velocity will be 0, and at this point in time, the ball will have achieved its maximum height. So this is the max height moment. And my claim is that the area between underneath the curve here is the key to that, figuring out how high the ball has gone. And so just like we did with acceleration and velocity, we're going to treat the area between the curve and the axis as the accumulation, right? So because this is now the velocity curve, the area will accumulate. The area that's accumulating is height, right? Because remember, it's the accumulation of stuff that's changing, right? So acceleration is the change in velocity. So that accumulation of acceleration over time corresponds to velocity. And exactly like this, the rate and change of height is precisely velocity, right? Velocity is how fast and in what direction the height is changing. And so we're just going to accumulate all that rate of change, and that's exactly the area right here. Now, again, you're taking this, you've got to be like Lord Vaco in the Chronicles of Riddick when he's questioning that Lord Commander guy, or whatever his name, what was his name? The Lord Marshal. And he's like, you want me to take a whole frigate to chase down one man? And he's like, don't question it, Vaco. Take it on faith. So for today, just take it on faith. Yeah? Anyway, so in particular, right, so if this is true, and it is true, just believe me for now, then that means that if I take, this is the area after 1 second, yeah? And that's the height that is gained after 1 second. And so if I know that this is the maximum height here, also notice that this area is going to be negative over here, right? So after this, the ball is going to start dropping again, and it's going to start accumulating negative height as the ball starts to drop. But right now, from 0 until this point where the velocity equals 0, so from where time is 0 until velocity is 0, all of this time the ball is traveling upwards, which means all the area under here, think of it as height being accumulated, yeah? Now here, this would require you to calculate both a rectangle and a triangle. We'll get to that next time. But let's finish up just by finding the maximum height. So because the ball is going up this entire time, it's accumulating positive height this entire time, the area of this triangle will be precisely the maximum height. And so let's calculate the area of the triangle. Do you want to know the area of a triangle? Well, how do we find the area of a triangle? Triangle, so if we have a triangle, yeah. It's especially easy, this is a right triangle, I mean, it's always true, but so let's say this is the boss, and this is the height. Then the area is 1/2 le boss times el heito. So what is the height? This is 29.4 meters per second. And the base is 3 seconds, right? Because if we look over at Homeboy here, right, the base is exactly 3 seconds wide, and the height is exactly 29.4 meters per second tall. And so we multiply 1/2 times 3 times 29.4 seconds, meters per second. Yes? Yes, yes. Oh, that is how it's done. And then we have to calculate that, so I don't know, this is, let's see, 1.5 seconds times 29.4 meters per second. Let's Whip out the calculator. Burp. 29.4 times 1.5. 44.1 meters. That is the maximum height. Boo, boo, boo. Boop doo, boop doo. Boop boop boo, 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 boo doo. Boop 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 doo. So if you throw a rock up in the sky, that's how high it will fly. Okay, well, so I'm going to fix those slides because they're riddled with typos. Let me see what else did I write here. Oh, that's it. That's the end, folks. That's all she wrote. Cool. So next week, I'll actually justify this next week. I'll talk about why this actually is true. And then we'll finish deriving the height formula. And then we'll have everything we need, at least as far as vertical stuff goes, because we'll be able to determine vertically at any point in time the acceleration. We already know that. That's constant, right? It's negative 9.8 meters per second squared. We already know the velocity, right? It's the initial plus negative 9.8 meters per second times the number of seconds you've gone. Right? So we have our velocity equation, right? They're way in the beginning here. Wait, did I go too far? Nope. There. Yeah, so we have our velocity equation. And we have our acceleration equation. Next week, we'll justify the area claim and develop the height equation. And once we have those, we'll be able to answer quite a few problems. Lots of interesting questions. Themes, thoughts, and feelings. And now I'm going to go because I'm just rambling. Thanks for tuning in if you did. I don't know if anyone did. It doesn't look like anyone did. But if you did, I appreciate it. And I hope you have a wonderful day. And I'll see you later. Yeah.